So today we start third chapter, current electricity. Current electricity, and that's a very important chapter in class 12. Okay, in either JEE, Neet, or in board exam. That current electricity is a very important chapter, and also there is a 2 or 3 numericals each and every year you get in board exam or JEE, Neet exam. Okay, that's a very important chapter. So here the name suggests the current electricity. So what is a current? So current is like there is a conductor, or you can also the another name is called wire. Okay, made by metal. And why metal? Because metal is a good conductor of electricity. Okay, metal is a good conductor of electricity. That's why we choose metallic wire. And there is a charge, okay, either positive charge or negative charge. So there is a electron move from, suppose here negative potential, here get a positive potential, so electron move from negative to positive. So electron is a, now here is a free charge. Electron is a free charge and move from negative terminal to positive terminal. And what is the positive potential here? That's the negative potential. Means negative potential phase to positive potential phase. The free charge, choose a free charge is electron. So electron move negative to positive. And here the opposite direction. Okay, the current flow opposite direction of electron moving. Okay, and that's the current I. There is a charge. Either if you consider the positive charge move from plus terminal to minus terminal. So okay, if a positive charge or positive free charge, so that's the current direction, and positive free charge direction are same. But if you consider the free charge is negative, so that's why the free charge direction either means electron direction and current direction are in opposite direction. That's the current I, that is equal to flow of charge. If you consider the negative charge or positive charge, just consider the flow of charge. That the Q is a flow of charge with respect to time, and this charge is free charge, and that's why you choose the metal. Okay, the free charge from metal is very easy. Okay, so that is I equal to Q by T, and we know that the basic equation from class 9, 10, and that is very common. Okay, and that Q is the free charge by time. So SI unit is the coulomb per second, and we get ampere. So 1 ampere equal to 1 coulomb per 1 second. If 1 coulomb charge move from one end to another end of a conductor in 1 second, so 1 ampere current flowing through that conductor. That's the basic definition of 1 ampere, and we know that actually. Okay, so current depending on the free charge and time, the very important factor, and that charge is now is a free charge, either electron or proton. Okay, if the electron move from negative terminal to positive terminal, means a negative potential to positive potential, means a lower potential to obviously higher potential. That's the lower potential here, lower potential, and you know that what is potential from second chapter, and that's the higher potential. Higher potential. So electron move from lower potential to higher potential, and current move from higher potential to lower potential, and like proton move from higher potential to lower potential. So now there is a little upgrade here. If here the small amount of charge, if I say that it is small amount of charge, delta Q move from, I consider that as the electron from negative terminal to positive terminal by small time interval delta t. So we get current I, and the current is a scalar quantity. Very important that current is a scalar quantity. Okay, so I equal to delta q by delta t. So delta q equal to I delta t, and now put limit both side. So dq equal to I dt. Now if you integrate both side, so integration of dq, I is a constant, dt, so q equal to I integration of dt. There's the finding of total charge moving from given direction of time, total time. Okay, that's the basic concept of current here. Now we discuss current density. Current density, and we know that what is current, and here the another name, the density. So density means there is an area. Okay, actually, suppose current per unit area, we get a current density. Okay, so current density symbol J, and that is a vector. Actually, current I, and the area also, area is a vector. So current density equal to current per unit area. Suppose you consider there is a flow of a pipe here, streamline flow here, and you see that like that. And here the area or cross section view, if you see that cross sectional view here, that is called A1, and here the cross section view is A2. So a number of flow of current. So okay, so suppose here is a much denser, okay, because area 2 is lesser than area 1. Okay, so J is inversely proportional of 1 by A. Is a less area means more density, and more area means less density. So they are inversely proportional. That's the current density. Okay, actually that's streamline flow and divide by permeate area, so we get a current density. And current density is a vector, so there is a direction. So if you consider there is an, suppose here we consider the plus charge here, sorry, plus potential here, and there is a minus potential, means there is a higher potential, that is a lower potential. So we know that from here, we know that current moving from higher potential to lower potential. So current move in that direction. Okay, so if I consider the positive charge, so that's why the density is in that direction. So current direction and density direction same. If you consider the free charge is positive, if you consider free charge is positive, means proton, and if you consider that free charge is negative, so suppose the electron, so electron move from lower potential, suppose there is a higher potential, there is a lower potential, so electron move from lower potential to higher potential. So that's why if you consider free charge of negative, so actually the current direction is opposite, so that is a J, that is a negative. If that is a positive, that is a negative. Actually, but mainly we consider that current direction I and the current density direction J are in that same direction. And if you consider the negative charge, it means an electron. So that is the opposite of current direction. Okay, that's very important. If you consider the electron, if you consider the free charge being electron, so J is a negative. Okay, because the current direction in left to right, higher potential to lower potential, and electron move from lower potential to higher potential. So that's that these two current density are in opposite direction. Okay, so if you consider the small amount of area, okay, if you consider there is a small amount of area, so I equal to J dot suppose small amount of area, that is called delta A. And if I consider the both are in same direction, okay, both are in same direction. So cos being 0, cos 0 be the 1, so J, suppose that dA, so it is I, okay, and if you integrate both sides, suppose a small amount of area, so you get a small amount of current, that is a D. If I put a limit both sides, we get, if I put a limit both sides, so the delta turn into D. Now integrating these two to get I equal to J dot A. So that's a calculus, mathematical calculation. Okay, that's very easy. But in physics, there is a J is a vector quantity, and J direction depending on the which free charge you choose. If you choose a positive, a proton, so electron direction of current and direction of current density both are in same direction. If you choose a free charge with the electron, so current density direction is opposite of the current direction. Okay, that's a very basic concept of current density. Now there is a unit, SI unit. So J equal to I by A. So very easy, that is I, we know that is ampere per meter square. There is a J, current density, SI unit. Now another concept we discuss, drift speed. Drift speed, and some books suggest that is called drift velocity, both are in same, okay, or velocity. Drift speed or drift velocity, the actual concept behind the speed and velocity is a little bit different, because speed has a scalar quantity, velocity has a vector quantity, otherwise the magnitude be the same, okay. Now, so what is drift speed? So in conductor, before we applying a potential, there is a free charge particles, they move randomly, okay, that direction randomly move, they move randomly in that direction, otherwise in that direction randomly, before we applying a potential here. Now if we put potential, suppose there is a higher potential, there is a lower potential. Suppose plus means the higher potential, minus being the lower potential. Now that free charge get a perfect orientation, okay, so actually move randomly, but not in haphazardly, so there is a drift. After applying potential, there is a drift. Before that, there is a no drift. Okay. Okay. So before that potential is a current with a zero. Before current with a zero, after applying potential, so there is a drift. So there is a current is not equal to zero here. That is before applying potential difference, called PD, and after applied potential difference. So after applied potential difference, these features get drift. Okay, but move randomly, but they tend and drift with a drift speed. So they move in drift and drift speed. So either that free charge, if we consider that is an electron, say moving haphazardly, but there is a direction. There's the direction, there's the direction, there's the direction, there's the direction on that direction. But there is a direction. Before that, there is a haphazardly, either plus minus haphazardly direction. Okay, no need direction here. Before that, before applied potential difference, there is a no need direction. But after potential difference, there is a direction. Okay, suppose the positive potential, negative potential. So positive V plus potential. So there is a electric field E, plus to minus direction. Okay, so now consider current density. So current density for positive charge. So there is a called positive. So J in same direction, and in the same direction. So current flow with the, so obviously same direction. I with the same direction. So current with the same direction. Electric field with the same direction, and current density for positive charge with the same direction. If I choose that is a free charge with a negative, so J is for negative in that direction, opposite direction. So here the free charge is mainly the carrier. These free charge is carrier. Okay, here the free charge is a carrier of carry. Okay, so by the convention, that's the basic convention. If I equal to positive, so there is a direction. Okay, there. So drift speed Vd here, the drift speed Vd, we get the, suppose the length of conductor be the L. Suppose we say that length of conductor be L, velocity equal length by time. Okay, length by time. The basic velocity formula has length by time. Now, if we consider the charge, the free charge, a carrier move from suppose this end, suppose the end is A to B end. If I consider the negative free charge carrier, or choose a negative, either free charge choose the positive, so B to A direction. So the free charge carrier, suppose there is a charge moving, that is N. Okay, number of charge carrier per unit volume is the number of charge carrier, either positive or negative, the number of charge carrier by volume. Okay, so that is equal to charge. Suppose there is a Q amount of charge by volume with a V, and if you see that there's a conductor, that's a conductor. The conductor is look like a cylinder actually. Conductor is look like a cylinder. Okay, means a wire, a copper wire or any metallic wire, copper wire look like a cylinder, and the volume be there's a cross section area A, and there's a length AL. The volume be the AL, or we know the pi r square is actually pi r square is the cross section area, or H be the L here. The volume of cylinder Q by A times L, that is the N. Okay, and the Q equal to NaL. Okay, and Q equal to, know that elementary charge multiplied here, that's a E, and here the E is a 1.6 10 to the minus 19 coulomb, the elementary charge here. Okay, and the current density. Okay, if you choose the current density, current per unit area here. If you choose the current density, the current here, that if you choose the current density, current per unit area, suppose J, that is I by cross section area be the A, and we get three equation: current density equation, drift velocity or called drift speed, length, conductor length by time, the basic velocity, speed velocity equation, time equation. We know that Q equal to NaL times E. Now here we know that I, there's that I equal to Q by T. The basic, first we discuss current equal to charge by time. We know that here. First starting we discuss current I equal to Q by T here. Now I equal to Q by T, and that Q equal to NA is the cross section area, L is the length of conductor, times E by T, and L by T, that is equal to Vd, drift speed, that is NAE Vd. So finally I we get NAE Vd, and okay, and if I A move from here, I by A, so we get NEVD, and you know I by A equal to J, current density, that is equal to J, so we get another expression J equal to NEVD, number of charge carrier, elementary charge and drift speed, so we get a J, current density, the current density expression. So here we see some expression J equal to NE Vd, and you know that current density is a vector. So V velocity, or if we consider this drift velocity or drift speed, so that is a Vd is a vector, and NE, that is a scalar. Okay, N is a scalar, and what is the NE? Now the another concept arises here. So what is NE? What is uh, N times E? Okay, what is NE? And see that equation. Q over AL, that is equal to NE. So Q is the charge and AL is the volume. So NE is a charge coulomb, there is a volume means per meter cube. Okay, coulomb per meter cube. So if N, so there is a for considered for free charge with the here the photon. So N with a plus N here. So there is a plus. So finally we get a modified this equation J equal to plus NE VD. So plus, so J and VDE are in same direction. So now if you consider that for electron, so N now the minus, so that is equal to J minus NE VD. So J and VD are in opposite direction. Actually, that is depending on direction. That is a what free charge you choose, either a carrier charge you choose, either positive or negative. Okay, that's the direction. Clear? That's a we get a J and VD expression. That's very important. And we know that as current density is a vector quantity. Okay, clear? The concept of current density, relation between the current density expression here, a new expression. Now we derive Ohm's law from here. Derive Ohm's law. How we derive the Ohm's law? So we know the expression of I, that is NAEVD. Okay. So here we know that is a find that expression for VD. If you consider a charge, uh, suppose a metallic wire, the cross section area be the A, and there is a suppose say that suppose that is a positive terminal as a negative terminal. So electron move in that direction. So that's why the current move in opposite direction I. Okay, and if you choose the plus photon move in that direction. So J plus in same direction and J minus for in that direction. Okay, so here is a free charge moving. When we apply the potential difference between these two terminal of a conductor, there is a generated electric field E, and now that the free charge is either you choose a proton or electron, they are moving. If they are moved, so we get suppose they are moving. So here we apply the Newton's second law. So that is equal to F, that is equal to mass, consider that for suppose consider electron, that is ME times acceleration, that's the force on there's here the free charge. Now from Coulomb's law, and you know the electric field, that is equal to F equal to E, the charge, times E. And if you choose that is a test charge, that is the test charge. So electron best that's a free charge carrier, free charge carrier be treated as test charge, that is QE. Okay, and there is a VD, the drift speed or drift velocity. The VD is a length of conductor, and by time we know that. And another expression from we know that acceleration times tau. And what is tau? What is tau? These are the called tau, and this tau is called relaxation time. Relaxation time. And what is relaxation time? Relaxation time is that when the free charge carrier move from one end to another end, so there is a collision. There is a collision between these two free charge carrier. And here is a billion number of charge carrier. Which is a billion number of charge carrier, they collide to each other. So if two collision, actually time taken between these time taken of two collision in that time means time taken between the collision, okay, or mid time taken for two collision, okay. That's the relaxation time, and that time there is no collision occur. That time is very small, okay, 10 to the minus 12 or there that time order, 10 to the minus 10 order, okay. Here is a no collision here, okay. Time between two successive collision, time between two collision. Okay, time between two successive collision is called relaxation time. We know that velocity by time, that is acceleration. Now this acceleration is replaced by F by mass of electron times tau, that is Vd, and that force, that's from Newton's second law, and that's the electrostatic force on that free charge carrier be the same. Now F is replaced by E, that's the test charge, E by me times tau Vd. So you get a new expression of drift velocity or drift speed. Now that expression we put this equation, I equal to NAEVD, and we know that I equal to NAEVD, and VD equal to we get NAE, capital E, mass of electron times relaxation, okay, relaxation time. So we get E square N A E by ME times tau. Okay, so now rearrange E square N tau by ME, and here is AE. Okay, and here see that E, we know that is a constant term, 1.6 into 10 to the minus 90 coulomb, a number of free charge, and tau is the relaxation time, that's the constant, and there's a mass of electron, we know that that's a constant. The whole is at a constant term, and that E square N tau by ME is another name, is called conductivity. That's called sigma, is called conductivity, sigma. And reciprocal of conductivity 1 by sigma is another name, is called rho, is resistivity. The reciprocal of conductivity is resistivity. So I equal to, here there is sigma AE, and now if I replace these, I equal to, that's the sigma replaced by rho, A by rho E. There is an E, and what is E? Electric field. And you know that electric field equal to V, potential difference between two conductors, that is V by L, length of conductor. So I equal to A equal to V by L, so by rho L times V, and that is a constant. So I times rho L by A equal to V, and if I change these, so V equal to rho L by A I. So now There is a constant, the resistivity, length of conductor, cross section area of a conductor, V proportional to I. That's the Ohm's law. That's the Ohm's law, and that's a constant term. A constant. A constant. And there's a directly proportional. There's a proportionality constant. And that proportionality constant is another name. The proportional constant is called resistance. The constant, another name is resistance. That is equal to rho L by A. So rho is the resistivity. That's the material property, so a metal property or material property if you choose. Okay, because the metal is a good conductor of electricity. That is the length of conductor and the cross section area of conductor. You know that. So there's that L. Okay, and the material if you choose the copper is another resistivity. If you choose the aluminum, that's a different of resistivity here. So that is equal to V equal to IR. That's the Ohm's law, as the very famous Ohm's law, and the resistance. So SI unit of resistance equal to R equal to V by I. V stands for volt SI unit and I with the ampere. So volt per ampere is another name from Ohm's law, that is called Ohm. The SI unit of resistance is Ohm. The symbol is look like this. So SI unit of R is Ohm. That's the basic concept. Okay, and that's the basic third chapter. Here we discuss, summarize the today's class. If I summarize, so we start from current electricity. What is current here? You know that concept actually in class 9, 10 or 8. So here is get another expression for calculus mathematically. And what is current density? We derived some expression of current density. Actually current density equal to current per unit area. So current density is a vector and current is a scalar quantity. We know that. And that is a J. The SI unit is ampere per meter square. Another concept we derived, that is a drift speed and drift velocity. Okay. So we clear that concept, what is drift speed and what is drift velocity. Actually both are same, the magnitude are same, the velocity there is the direction, otherwise speed and velocity magnitude be the same. So concept of drift, we relation between current density and drift velocity or drift speed relation, and what is the direction of J and BD depending on free charge carrier. Okay, either for charge carrier be the positive, so J and BD are in the same direction. If charge carrier be the negative, means the electron, so both are in opposite direction. Okay, we derive that, and now we derive the Ohm's law, very famous Ohm's law. Okay, and put some basic equation from these force we get from Coulomb's law, electrostatic force of Coulomb's law, and that's the Newton's second law, and that's the velocity, acceleration, and tau, relaxation time, the time taken between two successive collision. Okay, there's the tau, and tau is the time with the tau is and is a second, that is velocity equal to at. So now a is replaced from Newton's second law, F by mu, and now this F is replaced by that electrostatic force, that is E times E, and we get Vd expression. Now Vd expression put in this equation. So here we get some constant term here, like E square. Okay, that is 1.6 into 10 to the minus 19 coulomb. Total free charge carrier, either positive or negative, doesn't matter here. That is the relaxation time, collision between two successive time taken for two successive collision. That is the mass of electron, and that is the cross section area and electric field. And we know that previous chapter from potential, that is electric field, that is equal to V potential by L. Okay, so here the L is the charge conductor length. So now replace, that is E equal to here V by L actually, and that expression, that is all constant, that expression is called conductivity. That's very important. The expression is new name, we know that, that's the conductivity. The symbol is sigma, and now there is a resistivity, that is a reciprocal of conductivity, and so that is A by rho times E, and it is V by L. And if I put in that direction, that is rho L by A. Now change that. So rho L by A, if I remove that, that is a constant term. Resistivity, there is a depending on material property, length of conductor, cross section area of conductor. These all three are terms are constant. So if I remove this constant, we get a proportionality. So V proportional to I, that's the Ohm's law. Okay, and the proportionality constant is another good name is called resistance. Okay, so that is equal to V equal to IR. So A sine of R equal to V by I volt per ampere. The name is ohms as a symbol. Okay, that's the basic concept of today's class. If you have any doubt in that section, always ask in comment section. I will try to give the answer. So today in the class here. Thank you.